I didn't get to finish this off from last time, right? What were we looking at last lesson? Does anyone remember?
Yeah, exponential growth.
Yeah, and how would you describe this concept of exponential growth?
Well,
It's a constant growing rate or something.
Is it a constant growing rate?
No, it's a changing growing rate.
Yeah. Watch for
Isn't
now.
it like the
yeah,
2, 4, 8, 16? Is that what it
It's the
is?
same as gradient.
So
It keeps growing, but it like.
so that's like doubling each time, and that could be an example of that, right?
Yeah.
A special rate of
essentially,
change.
What about
Essentially.
1, 1, 3?
Essentially, if I can draw a graph here, and it exhibits some kind of growth that resembles this shape. In particular, there was an equation that went along with it. So, can you find that equation for me?
P-O-E-K-T.
Okay, so we said P, and I used P for was like population. One example that we looked at is equal to P sub 0. So that's like the initial
KT.
amount, E to the power KT, right? This was an equation that could describe an example of exponential growth. The idea was that the more of something you have, the faster it's going to grow. Okay, and the example we used was like with population.
Bacteria.
Okay. Yeah, and bacteria as well. If you look at like cell division, right? The more cells there are, and the more that they divide, obviously, the faster they're going to grow. What I didn't get to look at was looking at things the opposite way. What happens if I start losing things, right? Instead of growth, I could have decay. Exactly. What would that look like, and how do we describe that? Fortunately, it's a very similar concept.
The absolute other way from that one.
It's a very similar concept, yeah. And we can keep the equation in the same way. We're going to use those same initial conditions and same kind of equations, but the graph is going to look differently if I actually plot it. Yeah, where would I flip it?
On the other side.
It's like to make the parabola, sir.
I just kind of flip, yeah, I mean, it does resemble that shape, but it's not exactly a parabola, okay? So it would look something like this.
yeah.
Okay. And I'll show you some examples of graphs that use that kind of this kind of shape here. For now, though, let's look at a very simple kind of question. Okay, we can always get different types of information when we're looking at questions involving exponential decay. Here's a very simple type. We've got a mass of a radioactive substance decaying exponentially according to this equation. Okay, m is equal to 100 e to the negative 0.04 t. Okay. So I've got that equation there, and I want to be thinking, okay, how can I find its initial mass? So anytime I'm thinking of initial, what am I really thinking of?
Start.
At the beginning, right? And because I know that t is talking about time,
You can equal that to 0.
yeah, I can say, and remember, it's really important you communicate this.
I think it's 100.
When t is equal to 0,
So what is that?
then m would equal to, what did you say, Dylan?
What's that above the
100.
100, right? Another thing you could notice is because if we come back to this exponential decay formula, right, you can notice that, hang on, p sub 0, or the initial amount, is still that constant which is in front of your exponential expression. Part B, okay, what was the mass after 10 years? Again, we're not going to have to do anything different here, right? I'm just going to say when t is equal to 10. And I'm going to substitute into my equation. I'm going to get some mass, right? Can you calculate that for me?
No.
Yeah, please.
So it's 67.
Okay, 67, give me some decimals.
0.032.
If the question year 12 doesn't really specify, I mean, just the 2 decimal places would be fine, right? So in this one, the question is mass in grams, so let's just say 67.033 grams. Okay. Now, let's finish it off. Remember, the idea is that the rate of change, or the amount that this piece of radioactive substance is decaying by, is related to how much mass there is. Okay, so the more mass there is, the more or the faster it's going to decay. This question is asking me now: show that dm dt is equal to this expression, and also find the rate that the mass was decreasing at 10 years. Okay, so they'll often ask questions like this, where they ask you to show things or show that an equation satisfies things, and it's a different type of question. You're not actually trying to find anything. They've given you a result, and you need to actually, you need to actually show that. How could we go about doing that, do you think?
Right, the original. Oh, yeah.
Wait, you can't.
Find the derivative of the original.
Good, right? So a really big clue is, okay, I've got m here. Let's find dm dt. That's just taking the first derivative. So I go to this part. I start with m is equal to 100 times e to the negative 0.04 t. And if I'm taking the first derivative, what am I taking the derivative with respect to? Just t, right? And it's really easy with, remember, exponential functions. I'm just going to take this coefficient down, okay, or take the first derivative of this. So 0.04, and I'm going to multiply by the original function. That's the first derivative, right? Now, in their one, they don't really have many numbers, right? They've got negative 0.04 m. Where's m going to come from?
Start m equals 100.
Right, yeah. Come back to the beginning, and you notice this portion here, well, I can see that. That's in my first component. That's in m, isn't it? So that's how you can easily show that dm dt is equal to negative 0.04 m. Okay? And that's all you have to do. Lastly, they say, hence find the rate which the mass was decreasing at. Now, what you could do is you could go to your dm dt, your rate of change, and substitute in t equals 10 into this equation. Is there an easier way to do it though?
Why is
Just
it
take the.
Take the what?
67.03? Because
Yep.
that's 10 years.
And substitute into this equation. Remember, the idea is that your rate of change is changing according to how much mass that you have. And because the question is kind of leading you into it, they've already asked you to find the mass here. You can take this value and substitute into here. And just be careful, you don't really want to round or anything yet. Just make sure you keep this initial value. Maybe you can store it, or you can punch in this guy again. But make sure that you actually have the full decimals there. Question?
How do you get 0.04?
Because remember, when you take the derivative of an exponential, right, what I'm going to do is I'm going to take the derivative of this part here, which is negative 0.04, bring it as a constant at the front, okay? And then that's what I get left with there, and the original front. Yeah.
Couldn't you just like the 100 minus 67.03
Yep.
and then divide by 10?
Because...
10 years.
Okay, that's an interesting question.
Would that work, or because it's exponential?
Okay, so I think you're answering a different question here. What you'll notice is that the rate at which something decreases is not constant. It's not decreasing. It would be a straight line if it was. And also, this is not asking for like the mass of it anymore. It's asking for the rate that which it's changing at. So what does this actually mean when I substitute it in? Nathan, what value did you get?
Negative 2.68.
Negative 2.68?
Yeah.
Okay, let's say grams, right? What this is saying is that at this point in time, at 10 years, how much is the mass of the radioactive substance decreasing by? It's decreasing by it's decreasing by 2.68 grams each instance. Right? Does that make sense?
Is
So-
that per 10 years? Or is that
No, that's only at that time. That's only at that time. That's a really good question. It's only at this time.
Because of all that's what we're, yeah.
Exactly right. Remember, if something is changing according to how much stuff there is, obviously it's the rate at which it's going to be changing is also going to be different at each time.
Oh.
Yeah, because when we looked at that initially, if you found the derivative in the initial time, it would be much faster. Like, it'd be decreasing at a much faster rate.
Yeah.